Hello, students. Welcome to this lecture in which we continue with calculus. Now we're going to set up a new problem a little bit different than before. We would like to find the slope of a tangent line at any point xy on the curve y equals to f of x. So our new problem will look like this. Let y equal to, let f of x be equal to x squared like before. We have to find an equation, but as you remember, finding equation is pretty much the same as finding the slope, right? Because if we know the slope, we know the equation, right? Find an equation of a tangent line, maybe the tangent line, or the tangent line at x comma y. As I remember last time x, y was set to be 1 and 1, but now it could be any point that we want. Okay, this is from the last time. Okay, so let's slowly start building this problem up. So we have a function which is a quadratic function. If you remember, the shape is something like this. And suppose we have some point which is denoted by x here and y over here, and usually we call it x comma y. So we would like to find an equation of a tangent line, so the line that goes something like this at any point x. So x could move around from left to right. And as we agreed last time, if we have only one point x, we can't really find the equation because we need 2 points to find the slope, right? So what we did last time, we moved a little bit to the right. It doesn't matter to the right or to the left, the answer would be the same. So basically, we're going to select some second point over here, which we will call x2, and we're going to go up to the function. We're going to select this point. This would be y2 over here, and we're going to draw a line between these 2 points. So I'm going to draw the line between these 2 points. As you can see, my blue line is not far away from red line, and my ultimate goal would be to take x2 and start moving it towards x. And when they will be really close to each other, this blue line will try to approach the red line, right? It will be very close to the red line. And that's the whole idea of the procedure. We move x2 close to x, and blue line moves closer and closer and pretty much matches up with the red line. Okay, so let's take this distance over here and call it delta x. And delta x pretty much is, delta x is just x2 minus x1. All right. So last time what we did, we solved for x2. So solve for x2. So if we add x1 to both sides, we're going to get that x2, this term, is equal to x1, which is on the left side now, plus delta x. So this is our formula for x2. So basically what we do, I said x1, but it's actually just x in our notation. So we take x, we add delta x to come to this point over here. So we start, I'll use a different color. So we start over here, we make a delta x step to the right, which is this part of the equation. We arrive to x2. Graphically, it's really easy to understand. So we would like to build our slope. Again, our slope is y2 minus y over x2 minus x, which is y2 minus y over delta x. So the only thing we don't know in this expression is y2. So let's calculate y2. So to calculate y2, we have to take f and take x2 and plug it into f. So it's going to be f of x plus delta x. F of x plus delta x. All right, so let's try to calculate this. So our function is x squared, so we take x plus delta x. So f of x is equal to x squared, right? So we're going to take x plus delta x and plug it in over here for x. So that's what we get. And then we apply our famous formula for a plus b squared, which is a squared plus 2 times a times b plus b squared. So we calculated this quantity. So we're gonna and actually why did we do that? Because if you think about it, this is y2. Let's look at the function. So you take x2, you plug it into the function, you're gonna get y2. So we have y2 equals to f of x2. All right, so now we have y2. This is this quantity, so we're going to take it and plug it back over here. So we have equal sign, we have x squared plus 2x delta x plus delta x quantity squared. Then we have the minus from here, so minus and y. But let's think what y is. Y is just f of x, which is x squared, right? So again, the same procedure. We take x, we plug it into the function, we get y. So we plug in x over here. So this is our expression for y. So we plug in x squared for y, divided by delta x. And the hint is the term after the minus sign should go away. What do I mean by that? I mean that we have a positive x squared up front, we have negative x squared at the end, they add up to 0. So we're left with 2x delta x, then we have delta x squared divided by delta x. We can clearly see that delta x is a common factor, and I know a lot of you want to do this right away, but that's not legal because we have a plus sign in the middle. So we can't really cancel this delta x out. And in general, word cancel is really, in quotes, bad word because we're not really canceling, we're trying to divide. In order to divide, we need a product. So what I'm going to do, I'm going to factor out common factor delta x, and I'm left with 2x plus delta x divided by delta x. So now I have a product, and if I have a product, I should be able to divide. But when I divide, I should be clear that I'm not going to be dividing by 0. So let's look what delta x is. Delta x is our small step to the right. So step cannot be equal to 0, because if step is equal to 0, then we don't have x2. So our delta x is really small number, but it's not 0. So it allows us to divide it out. So we have 2x plus delta x left. Now we're going to do a lot of hand waving. So what is delta x again? Delta x is very small. Very small. And we're going to try to make this procedure a little bit more mathematical in the future. Actually, that's our next step pretty much. We'll do a few more examples and then we'll try to create this procedure. What do we do when delta x is really close to 0? But what it tells us that our slope is very, very, very close to x. It's not exactly to x because we have this delta x, but delta x is such a small number that it doesn't really affect to x. So what is m? M is a slope at any point x comma y. So we found it for any point x, y. You give me x equals 1. If x is equal to 1, then the slope is very, very close to 2 times 1, which is 2, like last time, last lecture. Right, if you tell me if x is equal to 3, you get that m is pretty close to 2 times 3, which is 6. And if you look at the graph of the function, you see that the slope keeps getting bigger and bigger if we move up. Like if the function keeps growing, our slope also gets bigger and bigger, right? The steeper and steeper. Okay, and can we use a negative value? Why not? If x is equal to -1, you get slope to be pretty close to 2 times -1, which is -2. But let's look at the picture. If you step to -1, your slope will be like this, which is a negative slope. Okay, so let's do one little exercise before we move to some notation that we need to define. All right, so small exercise tells us find an equation of a tangent line for f of x equal to x squared at x equals to 5. So we know from the previous exercise that m is pretty close to 2 times x. If x is equal to 5, this implies that slope is pretty close to 2 times 5, which is 10. All right, so our point xy is x equals 5, but we don't know the y value. So to calculate the y value, we need to calculate f of 5, which is 5 squared, which is 25. So we plug it in over here. All right, this is our point. So we can use point slope form. Why point slope form? Because we have a point and we have a slope. That's straightforward, right? So y minus 25, let me remind you the form. Y minus y1 m x minus x1, where x1, y1, any point. And our point is 525. So y minus 25 equals 10x minus 5, and that's pretty good enough. All right, so let's solve this exercise because we did this part in the previous exercise. So let's talk about notation a little bit to finish this lecture off. So what would be our notation for this procedure? So the function 2x that we found is called the derivative of y equals to, maybe in the next line. So y equals to f of x equals to x squared. And if the original function is written as y equals ... or f of x equals to ... so ... means something, then the derivative is often written as y prime or f prime of x. So you read it as y prime or f prime. So in our case, y prime is equal to f prime is equal to 2x. So the next question, how do we compute the derivative? So we compute the derivative of f of x by forming the quantity, and the quantity is a fraction. In the numerator we have f of x plus delta x. So x plus delta x means small step either to the right or to the left, minus f of x divided by delta x. And this quantity has a name, it's called difference quotient. All right, so we form the difference quotient, which defines the slope of a tangent line at x comma y. Then after we form the quantity, we figure out, and I'll put figure out, but in the future we'll try to make it more precise instead of just figure out what is a specific precise mathematical procedure. So we figure out what happens when delta x gets very close to 0. That's our procedure. Again, this also we need to define a little bit more precise, but that's probably a good place to stop, and in the next lecture we'll do an example from physics. See you next time.